Hey guys, welcome back. Today's video is about charges and Coulomb's law. The prerequisite knowledge you need to know is first, just a general understanding of the atomic structure, and second, how to deal with vectors. And what we're going to do is determine the elementary charge, and we're going to use Coulomb's law to calculate the electrostatic force. Now first, let's talk about charges. Atoms can be negatively charged, neutral, or positively charged depending on how many electrons they have and how many protons they have. The atom you have in front of you has 3 electrons and 3 protons. Therefore, this atom is a neutral atom because it has as many electrons as it does protons. If it had more electrons, it would be considered negatively charged. And if it had more protons than electrons, then it would be considered positively charged. Now we can apply the same logic to objects in general instead of just atoms. So in front of you, you have a screen. On your screen, you have a picture where there is a group of trees with pluses scattered all over them, and the clouds above them where the lightning strike happens with a bunch of negatives. This just means that the trees are generally positively charged. This means that they have more positive charges than negative charges. And on the other hand, the clouds have negatives because they have more negative charges than positive charges. So the point is, objects can be charged positively, negatively, or neutral, just like atoms can. Now, you've probably seen this before in your studies of maybe magnetism, but what we know is that opposite charges will attract towards each other, they'll pull towards each other, and like charges will push away from each other. And just like every other push or pull in physics, these are forces. And the result of the push or pull as a result of charges is what we'll call electrostatic force. So if you're a positively charged object and you feel a force towards a negatively charged object, this pull is referred to as the electrostatic force. That's just what we'll call it. Now before we talk about anything with the electric force, let's talk about gravitation for a bit. Now the Earth feels a force towards the moon, and the moon feels a force towards the Earth. Now both of these forces are equal to each other, and what they depend on is the mass of the first object, planet Earth, times the mass of the second object, the moon, divided by the distance between them squared and multiplied by a constant. You may have seen this before, or you may have never seen this before. But first, I wanted to introduce this for a little bit because this is going to come very handy when we talk about electrostatic forces. Now I'm going to show you a simulation. So what you see in front of you are 2 objects. This white one here to the left, and this white one here to the right. These sliders at the bottom allow me to assign an amount of charge for each object. For the first object on the left, I'm going to give it 10 microcoulombs of charge, positive. And the one on the right, I'm going to give it negative 10 charges, microcoulombs, so it's a negative charge. Now what you'll notice already is that there is a force that each feels towards the other one, very similar to the Earth and the Moon feeling forces towards each other. What you'll also notice is that their values are exactly the same. So the amount of pull that this object feels from the other one is the same as the blue one feels from the red one. So the first thing is that if I change the amount of charge, we're changing the amount of pull, just like what would happen if you changed the masses of Earth and Moon. Their forces of gravitation would be different. Another thing we can change that would alter the force is the distance between them two. So as I increase the distance between them, the force was decreased. Now this is also true about planets. If the moon was further away from Earth, it would feel less of a force, less of a pull towards Earth because of its increased distance. Now just look at this equation one more time, and without blinking, look at this equation now. It's very, very similar. Instead of a G, there's a KE. This is also a constant. Instead of the 2 masses, we have the 2 charges, Q1, Q2. and over the distance between them squared. Now let me just talk about the details. So Ke is called the Coulomb's constant, and it's equal to 9.0 times 10 to the 9 Newton meter squared over Coulomb squared. This is just a constant. Ke is always 9.0 times 10 to the 9. Now Q1 refers to the charge of object 1. Q2 refers to the charge of object 2. And R refers to the distance between them. Fe is the electrostatic force. How much pull will they feel towards each other as a result of their charges? Before we can talk about using the equation and calculating how much objects will pull towards each other because of their charges, we have to talk about the measure of charge. So what I'm introducing here is what's called the elementary charge. And the elementary charge is the amount of charge that a proton or an electron has. This blue circle here is an electron, and this is a proton. But the value of charge is exactly the same for both of them. 1.6 times 10 to the negative 19 coulombs for both of them. What's different though is that for electrons, this charge is negative, and for protons, this charge is positive. So same value, just different signs. That's called the elementary charge. Now let's use everything we talked about to try to solve a problem example. What it says is sphere A has a charge of plus 6.0 times 10 to the negative 6 coulombs, and it's located 4 centimeters to the left of sphere B, which has a charge of negative 3.0 times 10 to the negative 6 coulombs. So here's my sphere A. Here's my sphere B. The distance between those two is 4 centimeters. And what they want to know is the force between them two. Before I attempt that, I just want to label that this sphere A has a positive charge because of the positive 6.0. So I'm just going to put a big positive in it. And this one has a negative charge because it has negative 3.0 Coulomb. So I'm just going to put a big negative in there too. Now what we need to find is the force applied on sphere A by sphere B. Let's write out Coulomb's law. The electrostatic force is equal to Coulomb's constant, multiply the charge of the first sphere, the charge of the second sphere, and the distance between them squared. Let's put all the numbers in that we know. Let's calculate it and let's see what it gives us. So Ke is 9.0 times 10 to the 9. This is a constant. The charge of sphere A is 6.0 times 10 to the negative 6. The charge of sphere B is 3.0 times 10 to the negative 6. Now, you may have noticed that I didn't include the negative sign in the calculation, and I'll talk about why in just a second. We're going to divide by the distance between them squared. The distance between them is 4 centimeters, but we have to change that to meters first. So we're just going to move the decimal over twice. 0.04 squared. Now if we put this in our calculator, what we'll get is 101.25 newtons. It's a force, the unit is newtons. Now we know how much the force is, but we also need to know what direction it's being applied. Now the reason why I didn't include the negative in solving is because we're going to use the negative and the positive to understand in which direction the force is applied. Because these charges are opposite, we know the force will be attractive towards each other. So the force that A will feel will be towards B. So the force that B causes on A is going to be to the right. So I'm going to say right here, to the right. So the force that A feels because of B's presence, will be 101.25 newtons to the right. Let's do question B now. It says a third sphere C with a charge of positive 1.5 times 10 to the negative 6 coulombs is placed 3 centimeters below sphere A. What is the new net force on sphere A? Let's draw a sphere. I'm going to make it red as well because red will be positive. We'll label this as sphere C. And we're going to say that the distance between them here is 3 centimeters. Let's label this A. So for B, first we need to find out what the force is that C applies on A. And then we're going to use that force plus the force from part A to find out what the net force is on sphere A. So again, we're going to apply the equation one more time. Q1, Q2 over R squared. This is a constant. It's always going to be the same. Q1 here will be 6.0 times 10 to the negative 6. Q2 will be the charge of C, 1.5 times 10 to the negative 6. And divide by 3 centimeters squared. Not forgetting to change that to meters. And we'll put this in our calculator real quick. (9.0) times 10 to the power 9 multiplied by 6.0 times 10 to the power negative 6 multiplied by 1.5 times 10 to the negative 6. Divide that by 0.03 squared, and we get a nice 90 newtons. Now that's the amount of force. We haven't told anyone where the direction was, so let's talk about that now. Again, sphere C has a positive charge, so it's going to be positive. Now what we know is that positive or like charges will repel each other. So I'm just going to draw an arrow that shows where the forces will be applied. C will be pushed away from A, and A will be pushed away from C. So the force that A feels is 90 newtons upwards. Now we're almost there. What we need to do is find the new net force on sphere A. To find the net force just means total force, we're going to add these two forces together. We have a force to the right, 101.25, and we're going to add it to a force upwards of 90 newtons. Now, if you remember from vector math, what this means is we have a right angle triangle, and what we're going to do is solve for the hypotenuse. So we know that a squared plus b squared equals c squared. That's Pythagoras, which means that c is the square root of 101.25 squared plus 90 squared. Calculating that really quickly. We get a value of 135.5 newtons. Now the last thing would be to find the direction of this force. So to do that, we're just going to use trigonometry. We have the opposite and the adjacent, so we can use the tan inverse to find out what the angle is. So angle theta is tan inverse of 90 over 101.25. That will give us a value of 41.6 degrees. All right, so we know that as a result of these two charges, sphere A will feel a 135.5 Newton force 41.6 degrees above the horizontal. Now with that, let's pause here and check for your understanding. First question asks, what is the electrostatic force? Second is, what is the elementary charge? And third is, what is Coulomb's law? To summarize this video, Coulomb's law shows the relationship between the electrostatic force, the charges, and the distances between them. Protons and electrons have the same value of charge, referred to as the elementary charge, but they're opposite in sign. Thank you for watching. If you have any questions, get them to me and I'll try to answer them as best as I can.